Before I introduce our speaker today, I'd like to acknowledge that the University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Puyallup, and Muckleshoot nations. We are pleased to have here today as our seminar speaker, Dr. Jessica Gephart, who is an assistant professor in environmental science at American University, where her research focuses on kind of the intersection of seafood globalization and environmental change, looking at how seafood trade drives environmental impact. Dr. Gephart received her PhD in environmental science from the University of Virginia and did a postdoc at the National Socio-Environmental Synthesis Center. She has served on the scientific leadership team for the Blue Food Assessment, and as I learned, seeing her face on Twitter last month in the White House, she is currently a U.S. Science Envoy for the U.S. Department of State. With that, I will turn it over to you, Jessica.
Great. All right, thank you all for being here today. I'm excited to talk to you about some of my very recent work on global blue food trade and its role in sustainable food systems. So this is some work that's been going on for about a decade now in the development of this big trade database that I'm going to show you today. And we finally have some of the results. So you're among one of the first cohorts to really be seeing some of these figures. I will start off by talking about some of the background and motivation for thinking about blue food trade and specifically about its role within sustainable diets. Then I'm going to give a brief overview of some of the methods for estimating blue food trade and hopefully give you a little bit of an appreciation for why it's so hard to get a sense of what seafood is coming from where and going where. Then I'm going to give an overview of the recent trends within blue food trade, talk about some of the shifts in trade flows, and then move on to seafood consumption, which is the trade and supply component and supply diversity. I'll then end by talking about some of the key messages and just highlighting a few of the case studies that students have been working on that draw from this database. So starting off with some of the motivation for this work, why are we interested in trade? Well, blue food has, the consumption of aquatic food has been increasingly looked to as for its potential role in sustainable diets. And by that, I mean the opportunities for it to improve nutrition while reducing the environmental pressures stemming from production. So looking across all blue foods, people have been saying, okay, on the health side, there's some real potential for the role of aquatic foods in sustainable diets because they are extremely dense in micronutrients. So in areas where they're experiencing micronutrient deficiencies, there's huge potential for them to be able to reduce some of those micronutrient deficiencies. Second, they're a critical source of essential fatty acids. And then third, they can play a role in displacing less healthy animal source foods. On the environmental side, there are also some really promising features for aquatic foods. So for capture fisheries, there's essentially zero or trivial land use or consumptive water use or nutrient emissions. So that's really promising when you think about those as major pressures for our global food systems. On the aquaculture side, there are, of course, a number of unfed farmed species that require very few resource inputs, and then many other species that already have really low feed conversion ratios, which means they have a comparative advantage in being able to convert feed into food, essentially. Looking across all of this work, though, when seafood are included at all into the sustainable diets literature, they're usually presented as just a single group or maybe a couple groups. So you'll see, chicken, beef, and all of your animals or all of your crops, and then there'll just be one group called seafood. Now, this is a really big problem because there are over 2,500 different species that are caught and farmed across marine, inland, and brackish habitats. So when you think about that vast diversity of species that can be consumed and the huge differences in their production methods, you can imagine that they probably have really different nutrient compositions and really different implications for the environmental pressures stemming from their production. So whenever we're lumping them all together in just one group, it's masking that diversity, and therefore it's really limiting our understanding of the potential of this food group as playing a role in improving sustainable diets. So this was really a big motivating factor for the Blue Food Assessment, which sought to disaggregate a lot of these blue foods and improve our understanding of their potential role in sustainable diets. On the nutrient side, this is a study that I was involved with, led by Chris Golden, which compiled nutrient composition data from across aquatic foods, but also terrestrial foods, to look at their micronutrient density. So here you have, along the y-axis, different animal source foods. Along the x-axis, a selection of different micronutrients here, with the darker colors indicating higher densities of those micronutrients as a percent of their recommended intake. And so one thing that you'll see from looking across this figure is that many of the blue foods here, colored in blue, are ranking at the top. So the order here ranks them in terms of their overall micronutrient density. So you see many blue foods outperforming a lot of the terrestrial foods in terms of their micronutrient composition. And this is really critical because it suggests potential for many of these species as being an important source of nutrients, but also it allows us to see that there are differences among aquatic species, but also looking across any given micronutrient, they can play a very different role in which micronutrients they're supplying. So taking that away and then turning to the environmental side, there's a similar problem where many studies have lumped them together as a single species or species group. This was a review that I was part of in 2019, looking across the life cycle assessment literature to see the representation of different foods in these studies and look at which kinds of environmental pressures were included. And so when we look here at the set of aquatic foods, there's actually just a handful of studies that include them at all. And most of the studies looked at greenhouse gas emissions alone. And so building off of this, we really wanted to think about how can we improve our understanding of the aquatic foods and what pressures they may be placing on the environment. Of course, aquatic foods can result in a wide range of different kinds of environmental pressures. So this is, we took a step back to think about what kinds of environmental pressures might we think about for both farmed and capture fisheries. On the farm side, many of the different environmental pressures actually mirror the kinds of pressures that you would see for agriculture. So land use, freshwater use, antibiotic resistance, genetic pollution. They can differ in some of the details, but a lot of those are somewhat comparable to the rest of the food system. On the capture fishery side, they tend to include some pretty different kinds of environmental pressures, especially relating to biodiversity and food web alterations. Many of these kinds of pressures are really not entirely comparable to what you would look at on land. And so in this study, we really wanted to focus on the big environmental pressures that we think about that are fairly comparable across the food system. And that's greenhouse gas emissions, land use, so terrestrial land use, and then nitrogen and phosphorus emissions, and freshwater use. One of the big issues for quantifying these different measures is that previous studies that use life cycle assessment data, oftentimes what they do is they just take what's the end estimate out of the model. So you can imagine running through all of the data about how a farm's operating, and you get one value out about greenhouse gas emissions. So a number of studies kind of took those end greenhouse gas emissions values and lumped them together to say, okay, this is probably the greenhouse gas emissions for, say, farmed shrimp. The problem with this, though, is that the different life cycle assessment models have really big differences in their underlying assumptions. So bear with me for a moment here, but there's no true greenhouse gas emission single number for shrimp production, okay? this is it, what number you get out of it all depends on many of the assumptions that you make about how to allocate sort of the greenhouse gas emissions along the supply chain. And so these kinds of differences become really important. If you say we take the greenhouse gas emissions of the forage fishery that are going into the fish meal that are then going into the aquaculture, you have to decide how to assign greenhouse gas emissions to that fish catch. Do you do it by mass and just divide it up? Say it's a fishery where the primary product is going for sale, but the trimmings are being incorporated into the feeds. Do you just allocate it by mass? Do you do it by value and essentially assign no greenhouse gas emissions to those trimmings because they would have been thrown away otherwise? It's a philosophical question about how to sort of ascribe blame in a way for the emissions of these different products. And so there's no single right answer to it. But the big problem is that some studies do it the economic way, some do it by mass, some do it other ways like by energy use along the supply chain. And so it becomes incomparable actually to take the output of one life cycle assessment model and compare it directly to the output of another. These decisions become really critical. So what we did in this study was we actually took a step back to create standardized resource use and emissions estimates for fisheries and aquaculture. In order to do that, we really had to develop a simplified environmental impact or pressure model. And then we compiled all of these life cycle assessment studies, but rather than taking out the end number, we extracted the input numbers. So we used all of the information about the farm operations, so that way we could run them all through the same model and actually get standardized estimates for these pressures. So with that, we then estimated these resource use and emissions environmental stressors within a hierarchical Bayesian model. And the data that went into this model included over 1,500 farms and over 1,000 fishery records. It included production in 29 aquaculture producing nations, which represented the vast majority of aquaculture producing nations. And overall, we wound up with estimates for 23 species groups that make up about 70% of blue food production. So the sample size is pretty good for many kinds of studies. What I will say is that these numbers are still pretty low, though, when you think about the global scale. So we do have fairly large uncertainty in many of the estimates, despite that. So here are the results from, or the output from this model. So these are the Bayesian credible intervals for the mean estimate of carbon emissions there in blue, farmed on the top, wild on the bottom, and then the nitrogen emissions in orange, phosphorus in pink, water use in blue, and then land use here in green. Now, notice that B, C, E, and F apply only to the farmed fisheries or farmed blue food production. The fisheries have essentially zero values, so they're not showing up there at all. The one downside of not just showing a bunch of zeros was that I think it was a missed point when in some of the media that those are in fact zeros. They're sort of implied. We didn't plot a bunch of we didn't make a bunch of empty plots, but maybe we should have to underscore that point. But looking across these figures, there are a few main overarching messages. So one, the greenhouse gas emissions for capture fisheries, they really span some of the lowest to some of the highest values across aquatic foods. And so that really suggests that we need this nuanced understanding of which species are being caught and especially which fishing methods are being used. The gear type is pretty influential for the greenhouse gas emissions associated with the wild fisheries. On the aquaculture side, overall, unsurprisingly, unfed aquaculture performs the best. We all pretty much knew that. That was an easy answer. What was harder was then getting this more nuanced understanding for the fed species. And there are some differences in the overall ranking for greenhouse gas emissions and nitrogen and phosphorus. The carps actually produced performing the best, whereas for land and water, the salmon and trout group was outperforming the others. And this came as a surprise to many people within the environmental space, but salmon's really efficient at turning feed into flesh. They're not using a lot of freshwater resources, and they're produced off farm. And actually the use of fish meal in some of these systems brings down your land and water use because you're not using crops. So those are some kind of surprising findings. The other thing that is notable here is that the tan bands represent the upper and lower bound for chicken, industrially produced chicken. So you'll see many of these different aquatic foods are either similar or outperforming the chicken production. Now, taking that together with what we learned about the nutrient content, this is now zooming in on aquaculture specifically, who looked at the relative nutrient content for each of those species groups here on the right, along with their environmental performance on the left, with the overall ranking being the order here across all, I guess, 9 of those dimensions. And one thing that we'll see is that every aquaculture group, except tilapias, outrank chicken, though of course you could get slightly different results if you decided to weight one of those categories more heavily. They have an even weighting here. Tilapias and chicken perform relatively similarly. And then unsurprisingly, you see bivalves and the carps there ranking at the top. There's a lot more to be done though in this space, and we've done a fair bit of work on the optimization of nutrient and environmental content simultaneously to start building more of that nuanced understanding in particular locations and for different populations. Now, looking forward at this dual role of meeting nutrition needs with a lower environmental cost, we need to now look into the future and think about the role of aquaculture in meeting these needs. And this is a concept of development known as nutrient sensitivity. And this work that I led here at Succinct was on developing scenarios for aquaculture and its role in human nutrition. And what this project did was worked with a lot of experts in the space to develop a framework for identifying the major drivers that are both uncertain and important in determining the overall direction of the future. And then we evaluated the potential for nutrients sensitive policies within that space. And the 2 axes that we came up with have to do with whether the system is regionalized or globalized, and whether it takes a growth first model to sustainable development versus a donut economics model where you're trying to stay above a social dimension floor and below an environmental limit. And so those 2 axes then create 4 diverging scenarios for this potential future role of aquaculture. The first here being this model of food sovereignty, which tends to be very localized or regionalized food systems that tend to be pretty diversified, focused on supporting and sustaining livelihoods and meeting those local nutrition needs. The endless, over here in aqua nationalism, we have these regionalized or localized systems, but that are really focused on boosting growth. And we have seen some hints of this in particular countries, including at times our own, of really turning inward for that growth and production. There's then the model of aquatic chicken, which is really about this endless growth and export model. So it follows a lot of the path of chicken of just produce as much as you can at the lowest price, with the idea that producing that cheap product will eventually be able to allow more people to afford the product and sustain their nutrition. And then finally, we have this idea of blue internationalism, which tends to be more focused on enabling trade and supporting diversity at the global scale, oftentimes thought of as this more high-tech kind of approach to production with some local protections in place for environmental and social goods. Now, one thing that came out of this work, of course, is that we've been thinking so far about this kind of environmental dimension, but the other really critical axis on here is this regionalized to globalized spectrum, and that's really going to reshape the kind of food system that we're thinking about. So turning our attention to trade, the core of my work is that we oftentimes think that we probably know a lot about global seafood trade. It's often stated as it's the most highly traded food commodity. It's of high economic value. And so one would think, okay, we must have really great information about what fish is coming from where and where it's going to. But this is actually not the case. Trade data, which I'll get into here in a moment, is much more complicated than that, and consequently has been studied in pretty aggregate or broad groups. So the reason this occurs is that there's just this fundamental mismatch between our global production data and our global trade data. So production data, as you're probably aware, gets reported in terms of live weight and as species or species groups, whereas the global trade data gets reported as products like fresh salmon fillets or canned salmon, and it gets reported in terms of product weight. Now, because of this mismatch, we wind up with a many-to-many matching problem where any one species can go into multiple products, and any single product can be made up of multiple different species. So if you try to pull kind of one thread and understand, well, what happened during this fishery collapse, you're going to suddenly be looking at many different trade codes, which also include many other species in them, and you're going to entirely lose the signal in that noise. And so that makes it really difficult to work with the trade data. And to make matters worse, many products are imported as one product, processed as another, that officially becomes a product of that country, and it's exported again. And so it becomes hard to link it back to its country of origin. This has really profound implications. It is difficult from the trade data as it stands to know some of the most basic things about our global blue food trade. We don't know from the trade data as it is how much of it is coming from farmed versus wild sources. We don't know whether what's being consumed is of domestic or foreign sources at a broad scale. It's really difficult to connect our trade to any kind of environmental change. And it's also really difficult to look at policy changes or certification impacts on these trade patterns. And so there's just this big gap that results from this data misalignment. That's been the core focus of this, the development of this database called the Aquatic Resource Trade in Species Database, or ARTIS. And this is an NSF-funded project. It's also received funding from EDF, Oceana, and Seafood Watch in order to produce this publicly available database of estimated species or species group trade going back to 1996 and expressed as live weight and in terms of nutrient content. Ultimately, this is going to become a publicly available database. Right now, we have the first version of the database ready. We're working on some publications and documentation and working to hire someone for the front-end development. So how do we do this? How did we solve this data mismatch problem? It essentially occurs in two steps. The first is solving a really big mass balance problem where we're trying to estimate the species mix in each product that's exported of domestic origin. We're trying to find out how much was being processed and which product it was processed into, and also keeping track of the exports that cannot be explained by production and imports alone. With those estimates, in the second step, we then connect those estimates to the bilateral trade data in order to disaggregate the trade data into species based on the appropriate species mix for that country of origin. So in that first step, we have to first define which species can go into which products. And we are then creating a big matrix of which species are allowed to go in which products. And we're estimating the proportion of each species going into that product while accounting for the processing losses. In this second column here, we're identifying which product can be converted into which other product. So a whole frozen salmon could be turned into a salmon fillet, but not vice versa. And you can't allow things to cross species. So a salmon cannot turn into a shrimp, for example. Then we allow a vector of products that are of unknown source, so they cannot be explained by the production and imports alone. And in some way, everything on the left here needs to be able to add up and explain our exports, also with estimating consumption. So the key thing that we're really trying to estimate here are the species mix for this given country's mass balance. So the species mix in their domestic products, the conversion of imported products to another, and then the consumption and error. So we solve this for every year, every trade code version, and every country. With those results, then we take it back to the bilateral trade data, and we first get the range of export sources. So even though you solve the mass balance problem, you can't say when you have a pool of goods that are being exported, how much came from domestic and how much came from imported goods. So what we do is we first fill up the exports with the domestic product, and then the imports, and then the error, and then we do the reverse process. And that gives us a range of the potential sources for each product. That then also gives us whether it was domestic or foreign. The domestic piece we can directly then connect to their estimated species mix. And the imported piece then we track back along the supply chain. So that allows us to then ultimately get to the country of origin and their appropriate species mix. Then what we take out of that is we compare the estimated species or species group name to the best resolution of that code. As many of you may be aware, a lot of global production data gets reported into very broad groups. And so we can, if there's a code that winds up with just austichthys assigned to it, we can actually compare that to the best resolution of that code. So if it's a tuna code, we can then reassign it. We then have done many stages or phases of checks of this data to make sure that the exports of domestic origin aren't exceeding the what was produced in that country, that all of the mass balances, that the exports that are processed and re-exported are not exceeding what was imported of the product. And we also then passed the results to a series of representatives from Oceania, from the different country offices, to get gut checks on the reasonability of these patterns. So we've been doing this iterative phase of checking the data. So we now finally, after about a decade of doing this, that started as a side project, now have some new results on some of the major blue food trade trends. And I'm going to highlight here some of the patterns and diverging patterns for marine and inland capture and aquaculture products. And so this is going to be, these are some fairly high level patterns, but I want to emphasize that these are things that we just could not know from the data alone as it stood in the aggregate form. And I want to highlight some of the ways in which the marine and aquaculture patterns really differ, and that even at that phase, it's really important to distinguish between what's going on for marine versus, or sorry, what's going on for capture versus what's going on for aquaculture. So the first point is that global blue food trade more than doubled since 1996, but we've had somewhat diverging trends here for capture versus aquaculture. So global capture trade has still increased by about 80%, but aquaculture trade more than tripled over this period. Capture fishery is still the majority of production, and recall that aquaculture makes up about half of global production, makes up about 30% of blue food exports. So we still see more of the capture fisheries being exported currently, but a much faster growth for aquaculture, unsurprisingly. You'll see a dip here, though, in 2020. There was a decrease in about 4% in exports overall in 2020 compared to 2019, but the aquaculture exports actually increased by 1.5% in 2020 compared to 2019. So this really starts to show some of the differences in the impacts that are being felt across these sectors and the very different responses across those sectors. We also, of course, see some pretty different trends in production by source as to what species are involved. So for looking just at these four groups, the top traded species are varying really greatly across the production sources. But when you look at the marine aquaculture trade, it is pretty concentrated across just salmon and white-leg shrimp there. So you see pretty high concentration in marine aquaculture compared to the other three sectors. And then when you look at the inland flows, they tend to be resolved only to pretty broad groups. And that has to do with the fact that there's a strong bias within both the production and trade data to have pretty vague reporting for inland production, and also pretty broad trade groupings for a lot of the products that these species and species groups are going into. So you wind up with actually quite a bit of uncertainty about what's going on the inland side compared to the marine side. When we then compare the trade to how much is being produced, we actually see a pretty stark difference of in the share that's being exported. So this is the proportion exported by source over time. We see that now around a third of all marine capture fishery production is being traded internationally, and that's compared to only around 7% of inland aquaculture. So we see this huge growth in inland aquaculture. We all kind of think it's driving these big global trends, but really a lot of that is currently being retained domestically, and only about 7% is being exported internationally. We'll see here a moment with the regional trends in that. When we compare this degree of globalization for our blue foods, we can see that compared to cereals, they were exporting around 10% in the late 1990s to around 17% in the 2020s. So cereals, which are often thought of as being this really highly globalized product, our marine capture is far higher than that. Marine aquaculture is about similar, a little higher, but our inland production is actually significantly less globalized or highly exported than the cereals. Now, why does this matter for the overall trade system? One of the big concerns that comes up often is the potential for trade to have a negative impact on the resilience and ultimately food security. So trade plays really cuts both ways when it comes to its role in resilience of the food system. Trade allows for a local place to access products from elsewhere in times of local shortages. So it can create that kind of buffer, but it also creates these risks of receiving propagated shocks. So if there's a shortage somewhere else and you're really dependent on those imports, you can wind up exposed to those shocks, and that can create this food security risk, as we saw with the 2008 grain crisis. So there's been some work on this, including some work that I've done that has been based on the network structures and some simple network models. And what this work has found is that net importers, developing countries, and those with low food stocks tend to be pretty exposed to these external shocks. And that some ways to reduce that risk include increasing the production diversity and sourcing diversity, and avoiding becoming too reliant on a single exporter. And so when we start to take some of those ideas about what structures might enhance resilience within blue food trade, we can compare to what's going on across these four subsectors of aquatic food trade. So when we look at the connectedness of the trade network, we can see here that the marine capture system is the most highly connected, with an average of about 40 partners, trade partners per exporter. But all of the networks have become more highly connected with an addition of about 10 more trade partners just over this time period alone. So we're getting this more highly connected system across all of the aquatic food trade. So it's becoming more concentrated or more connected, but it's generally becoming less concentrated. So here we can see that on the number of countries that make up 75% of exports, it's been about stable, had slightly, there's slightly more countries, which means less concentrated, making up that 75% of exports. But where we see this a much more decreasing of concentration, is that how we'd say that? Where we see, the less concentrated pattern more strongly is here on the imports, where the number of countries making up 75% of blue food imports moved from 12 countries in 1996 to 21 in 2019. And this is really reflective of the growing middle class in many countries. Now, if we look at this compared to crops, it is much more highly concentrated. So for wheat, there are around 7 countries in the EU make up 90% of wheat exports, and only 4 countries make up 80% of maize exports. So when you start to think about that as a risk, that is a much higher sourcing risk for wheat and maize than what we're seeing across aquatic foods. On the net import side, we see that North America and Europe are the highest net importers, not surprisingly. South America is the highest net exporter. And looking at the least developed countries as a whole, they're collectively net exporters across all of the production methods, and the net exports have tripled over this time period. Now, this may be a potentially good thing in terms of the resilience and reliance on imports for those countries. The flip side of that, though, of course, is the concern around the export of these nutrient-rich fish from these regions, which are really highly, have high rates of malnutrition, and that these foods could play an important role. So that's the flip side. And some of the work that we're doing now is really exploring more of that nutritional loss from these regions. Okay, so looking at collectively at these, the decreasing concentration is probably a good thing for the food system resilience, but as it gives that bigger response space in the event of shocks. But the increasing reliance on imports in particular regions can pose a risk. And it's really less clear whether or not these greater volumes of trade or higher connectivity ends up improving or eroding resilience as a whole. And one thing I'll say with this work is that a lot of this is still pretty theoretical, and there's limited empirical evidence for how these shocks actually move through trade networks. And this is one thing that's a really key piece of some of my future research. Okay, so now the benefit of all of this is that we're able to look at shifts in bilateral trade flows. So just at a very, very high level, realize there's a lot of information here. You can see that doing a Sankey diagram of the source to the importing region just for 2019, you can see that the patterns, even at this high level of trade flows, tend to differ pretty greatly. So on the inland aquaculture side, unsurprisingly, Asia is massively dominated. There is a pretty big flow to North America. But then if you look toward the marine side, Europe is a really strong player, both as an importer and an exporter. So the key takeaway from this piece is just that these bilateral trade flows are really pretty starkly different. And so it's going to vary which system you're focusing on, what patterns you're really seeing. Now, looking at these trends over time, you can see that the exporting region here on the y-axis and importing on the x-axis, what one would expect from trade theory is that you're going to have the highest trade flow within a region due to historical ties, common demand profiles, and lower transportation costs. We see that for Africa, Asia, and Europe, but pretty notably, North and South America and Oceania actually do not have the highest trade within region, and rather have their highest trade as exports to Asia. You can also see some of these really increasing, any of the orange bands that are increasing rapidly, like South America to Asia. That's that really big rise in aquaculture exports going to Asia. looking across all of these region pairs, nearly every trade pair did increase though. And so, so this has to do with that increasing connectivity and the increasing growth in trade overall. 2/3 of country pairs increased their blue food trade with one another. A notable exception at the regional level is North America to North America trade actually declined over this period. And it's the only one with a large decline. So we'll be looking into that one a bit more. Having this trade data, it allows us to start to understand consumption patterns. So if you're not working a lot with consumption data, it might surprise you that we have no real measures of consumption data. It's kind of just the error term on production and imports minus exports. So consequently, the trade piece is actually critical to understanding anything about what countries are consuming. And so by now having this data, we not only have the species level estimates of consumption, but we also are able to look at how much is coming from foreign versus domestic sourcing. So when I talk about consumption here, it really is just apparent consumption or supply, which is production and imports minus exports. Here, these numbers are expressed as the live weight equivalent. So it's not adjusting for the edible portion or waste. This is similar to what the FAO and other reports present. So now we can look at the consumption trends by source, and we've not been able to do this before at the country level. You can kind of do it at the global level without the trade data because if someone exported it, someone imported it. So you can kind of just take the production data and extrapolate. But we've not been able to look within any given regions or countries at their sourcing. So at the global level, you can see that blue food consumption overall increased, but capture consumption has declined over this period. And it's really been the growth in aquaculture, especially inland aquaculture there in light orange, that's made up for those declines. Across all of the regions, consumption has increased, apart from North America, which is relatively stable, and South America, which has had some slight declines, largely with those declines in capture consumption. The aquaculture supply increases are what are most noticeable really about these consumption trends. And you can see that it's, of course, most noticeable there in Asia, where it's been increasing really rapidly, but there have been large increases within North America, Europe, and Oceania, which have been offsetting some of those declines in capture fishery consumption in those regions as well. So with this information of whether things are coming from or having their country of origin connected to them, we're able to then look at how much of what's being consumed within a country is coming from domestic sources versus foreign imports. And this is really important because it allows us to keep track of the products that are being exported, processed, and then imported again in order to get a better handle on how much is coming from domestic production. So globally, the share of supply from domestic sources has been approximately stable. It's varied over time. A lot of that is driven, of course, by Asia, which has been extremely stable and very high domestic reliance within that entire region. But there is a lot of regional variation across when we look across these panels. So the yellowish or goldish line here is the domestic sourced consumption, and the blue is the foreign sourced consumption. And so we'll see that Europe here dominated by foreign supply, and then North America and Oceania having somewhat even levels of foreign and domestic supply within their consumption. The US here, we estimate consumption of 50 to roughly 60% for our middle estimate. Now, this number I pull out here specifically because you may have seen this number here in the headlines, that 90% of seafood consumed in the United States is imported. And you can see it across many different papers and across NOAA fisheries. You're one of your own very famous Twitter scientists here getting in a discussion about where did this number come from. And this really kicked off a question for me and Trevor and Holly to get to the bottom of it, because we'd all been sort of thinking that doesn't seem very plausible. And I had been thinking, I was never able to generate that number. I thought maybe I was doing it wrong, but I should probably get to the bottom of it. Because at the time, it was becoming really relevant within the policy arena. This number was being used to support a lot of policies that were being proposed. So you can see here in a statement from former Secretary of Commerce, Wilbur Ross, talking about using that number to support a lot of their priorities about boosting domestic production. It also then showed up within a presentation from NOAA about the priorities for reducing the seafood deficit, including things like opening up the marine monuments and increasing or streamlining the permitting process for aquaculture. So then when we started to dig into this number, we took a whole different method of trying to track the accounting of what was imported and what was exported, and what share that was being exported was being processed and brought back in. And this separate estimate, we reached an estimate around 62 to 65% of what was being consumed was foreign. And this really big difference from that 90% number didn't have as much to do with that foreign processing of products. That was a piece of it, but it actually had a lot to do with the live weight conversion factors that were being used, some of which were ones that had not been updated for decades and decades. One of which was just one that happened to have been written in law for some reason about what processing factor should be used. And so following this paper, actually NOAA updated one piece of their model, and actually it brought the number down significantly. So then kind of in the last piece of this issue with supply, one of the big concerns about global trade is that it leads to a homogenization of what's being consumed. So more people are all importing a bunch of tilapia. Maybe we're reducing the diversity of our diets overall. We started digging into this. This work is pretty ongoing because there's some real fundamental challenges with the diversity calculations, given the differences in taxonomic level that data is reported in. But so we're kind of still working this out with one method here. But what we're seeing so far is that the diversity of domestic sourced consumption tends to be greater than the diversity of the foreign sourced consumption when we go country by country. So that's suggesting that domestic production is contributing to greater diversity than what's being imported. However, when we look at the diversity of overall supply of what's being consumed in a country versus how much they're importing, we're seeing a generally positive association between those. That suggests that even though what you're producing is more diverse, you're still importing new things, and it's adding to the diversity of what's being consumed in that country overall. And so this is just one snapshot of that, and we're really disentangling this more to understand what's going on there. A key point with that, though, is that it's really important to maintain that domestic supply diversity and to not, in the longer run, let those imports to outcompete and displace that local diversity, given that that's what's really contributing more of the overall supply diversity. So a few key takeaways from this work is that overall, blue food trade has increased in terms of volume, connectivity, and how much is being exported at levels equivalent or exceeding agriculture. Consumption has increased overall, but that's really been driven by aquaculture, despite these declines in the capture fishery consumption. Individual countries, many of them are becoming increasingly dependent on these foreign source foods, but the degree of that varies greatly from region to region. And trade can add to consumption diversity, but it's important for it not to displace that domestic diversity. So with the first version of this database ready, with many, many analyses underway, there are a lot of collaborators that are eager to work with this data for a lot of different applications. And I've been having a series of different students working with me on different case studies that are little cuts of the trade data and digging into the stories that can be told with it in order to highlight applications of this data. So here are just a few different examples of some case studies that students have been working on, looking at coral bleaching and its impact on aquarium, fish trade, looking at comparing farm versus wild salmon farm trade, looking at disease impacts on exports, the one student that was in the early phases looking at Dungeness crab trade from the US, and then one looking at the trade impacts of the annexation or the Russian annexation of Crimea. And I bring up that last one because it's really important in the context of some current restrictions that we have on imports of Russian seafood. So it's the executive order from last March included fish and seafoods as part of the restricted goods that could be imported from Russia during the current war in Ukraine. And so looking back to the previous case of sanctions imposed on Russia and what happened with seafood imports, we can use that to start to try to understand what might happen in this current round of sanctions. So here we can see the different countries importing Russian seafood over time, with those that did not impose a sanction versus those that did impose a sanction. So those that did not impose a sanction, there's a slight dip there in 2014, but a pretty rapid increase driven largely by imports from China following the annexation of Crimea. Those that imposed a sanction had a slight dip and then is roughly stable following that. So they were essentially importing slightly less seafood, but that was more than made up for by the increases by China. Now, what did Russia do? Now, those countries that imposed a sanction here on the right, Russia largely stopped buying their seafood. So we see this huge drop in how much seafood Russia was importing from those countries. And that was more than made up for by imports from other countries that did not impose sanctions. So you see this kind of flip story where Russia basically started buying other countries' seafood and was able to sell its seafood largely still to everyone. But those that imposed sanctions mostly just weren't selling seafood to Russia anymore. With the trade database that we've developed, we can look what's happening, not just though with the direct partners, but also we can start to tease apart what's going on there with China. Is China really buying all of that seafood to consume? Or is there a chance that they're processing it and exporting it again to other countries? So this is not the time series of that, but this is fairly suggestive here in the case of the United States. The seafood that the US was importing from Russia, the majority of it actually all in recent years has come through China, not directly from Russia. And so this then creates a really big problem for those that are trying to enforce these sanctions and keep Russian seafood out of the United States. Then when we look to which species are largely involved, unsurprisingly, it's mostly Alaska pollock. And so that really suggests that's a place that one could look in more detail if they're trying to track down and think about how to enforce some of these sanctions further. So some of the key messages then, we have this database with many of these analyses underway. We're working on all of the documentation to make it usable and understandable, and hoping for it to then be publicly available within the next couple of years. The ultimate goal of this is absolutely for other people to use this data to answer their own questions about blue food trade and how it interacts with the environment and sustainable diets. So thank you all. Be happy to answer any of your questions.
Thanks. Any questions? Really, really interesting talk. How did you deal with food waste or with fish waste? It's been reported to be quite high, 30%, but presumably very few hard numbers on it.
Yeah, so the consumption numbers do not include consumer level waste at all. So it's all apparent consumption in the live weight equivalent. For processing losses, we include that within the model with the live weight conversion factors. We've compiled many from NOAA, from national data sources, and the EU has a pretty good data set on it. But the problem is that it's huge uncertainty in those live weight conversion factors. They're pretty bad. We know they vary geographically. We know they vary over time, and that there's no one really systematically collecting that data. So it's absolutely one of the biggest sources of uncertainty within this model. And I think I was explaining to someone earlier. Worse yet, it's not even just that they're outdated. Some of the product codes do have massively variable processing loss differences because you're dealing with bivalves, both shell on and shell off, in the same product code. You can't put a number on it. We don't know the share of shell on and shell off. Obviously, you're talking about a live weight conversion factor 1 versus like 15, and so there's a really big source of uncertainty for that, and it would be a good priority area for improving these estimates in the future.
So kind of a similar thread. Instead of looking at environmental costs for an edible ton of food, did you look at for actually consumed ton of food, and that might account for all the things that happen after we sustain, like food waste or global trade, say like shipping fish back and forth across the ocean, like greenhouse gas costs?
No. So the environmental pressure estimates stop at the farm gate within that particular analysis. So we wouldn't be capturing any environmental pressure associated with the loss and wasted food downstream of that. It's a really good question. I've done some of that work not for fisheries, but for the food system more generally. And sort of unsurprisingly, the waste rates vary a lot based on which product form you're talking about. So many people, of course, favor fresh foods and fresh fish, but the waste rates on them are much higher than other processed forms. So I would expect you to see really big differences for that. In terms of other functional units, so I showed the numbers for the per edible unit. We did also do per live weight, and we looked, but I don't think we put in the supplement, but we definitely looked at per gram and other functional units to compare the rank order difference. The biggest difference, I think, when switching from live weight to edible was with the tilapia, because they have pretty big heads.
Well, first of all, at President Falcon, I had no idea that our Twitter paper and PNS was such a tiny little component of everything you do on the paper. But my question to you, it's often said that although US wild caught seafood is really sustainable and well managed and everything, that what we eat is not sustainable because so much of it is imported. Is that true in the sense of, do we import the unsustainable food?
Yeah, so that's a key question of sort of where a lot of this work is starting to go toward. I have a project that's ongoing looking at food more broadly, but we're going to adapt the model to fisheries of developing a gravity model to look at where our environmental pressures are shifting, and essentially asking exactly that: are we shifting our environmental burden elsewhere, and to whom is it, and why? So is it because of lower environmental regulations, because of trade ties, regional trade agreements, standard economic features? So we're starting to get at that. We haven't answered it quite yet. A lot of the import for the US though is aquaculture, and so really it's not so much a substitution in the case of the US and say sustainable for unsustainables. Well, it might be, but most of the pattern is sustainably managed fish for farm fish, which just have very, very different environmental footprint profile. Yeah, great question.
Third quick question.
For this consumption, is this fraction of this is human consumption versus other uses of the fish? Is this only human?
This is all only human consumption. I've excluded fish meal and all non-human consumption out of this entirely. This is just human. The non-human piece is important, and we do actually we estimate that in the model, but then just for the purposes of presenting food, we exclude all out of this.
Right.
once spoke by a guy who worked for Mars, the Mars Corporation, who has 6 or 7 pet food brands, but they were the biggest purchaser of fish in the United States.
Yeah, so there's a code that I can't distinguish the pet food at that scale. You might be able to do for the US actually, but for the global one, it goes within animal foods broadly, so you can't distinguish which animal it's going to at that scale. But yeah, it's a great question, and perhaps you could do it for the US, or there might be a country that has their own national data to say. But
So, maybe this is related to that question. So you made the statement that trade seems to be diversifying our consumption profile, and that would generally be associated with an increase in resilience. My question is, are we importing things from a diversity of countries that are dependent on a few nodes of production for fish meal? So we're actually increasing our dependence on some very specific points, and thus are more vulnerable, although that's mediated by a diversity of production sets.
yeah, it's a good question. As far as I can tell, the profile of who's producing fish meal is actually expanding, and this is in part because there's been declines in Peruvian anchoveta. There are a lot of distant water fishing operations in West Africa that are expanding their fish meal footprint, but there are also a lot of producers in Europe and allegedly in Asia as well that have really ramped up their use of processing what would otherwise be waste in converting it into fish meal. And so it seems that actually the sourcing is becoming less concentrated. Now I say seeming because fish meal is both easy and difficult to handle. It falls within one trade code, so it's easy to know generally where fish meal is going, but theoretically there are lots of things that can be turned into fish meal, and there are lots of species that can be turned into fish meal. And so you sort of have a double-edged sword where it's like almost anything could become fish meal. Most things probably aren't because it wouldn't be economically sensible. So there's more uncertainty with fish meal than in getting to specific species and sourcing than with other things that are a little more resolved.
Yeah, what really, I was a bit confused about what the models were that these network models. I'm wondering if you could use those types of models to run simulations, for instance, if we had a really protectionist Congress that said we're going to eat 80% US seafood. Can you use those models to estimate where things will reshuffle and what the environmental impacts and economics will be in response to a policy like that?
Yeah, so most of the models that have been developed for looking at these kinds of shocks are, you can use input-output models. There are also some kinds of models that are more akin to agent-based models, but the way that most people parameterize them are based on the assumption of local linear behavior, and this is true for lots of economic kinds of models. If you talk about a really radical change, like we're suddenly going to close our borders, it's not that reasonable to assume some kind of linear behavior from such a large shock. And this is why we fundamentally don't have good empirical evidence for risks to big shocks. They're operating in the short term, so you're not talking about a long-term equilibrium. And you also have to have a shock that's big enough to detect, but not so big as to create a bunch of nonlinear behavior and responses. So working in the shock space when COVID hit and nobody could go out in the field, a lot of people were like, hey, Jessica, you work on shocks. We've got this big shock going on. We should study it. This must be perfect. And it's not, well, for many reasons, but it's not a perfect shock because it is so big and there were so many changes simultaneously and responses that create this non-linear behavior that you can't really finish a model or extrapolate from it. So you to back up to your question, we don't have a good idea about how to model a really large shock. We kind of play games with lots of different kinds of behaviors and then see what features tend to result in more risk or less. So you impose different kinds of behavior on it. For smaller shocks, you could use something like an input-output model, and that'd be the standard way that people would generally approach that.